So today's keynote is Dr. Tiago Quintino from the European Center for Medium Range Weather Forecasting. And it's really cool to have Tiago here. Weather modeling is a very hot area of research right now. And there's a lot of these big codes that are in C++. And so he's going to talk a little bit about that.
Hi. My name, as I said, Tiago Quintino. Thank you for attending. I'm, in a way, very thankful and honored to be invited by John and Joel to be here today. I feel part of this community, although over the years I have followed it closely, but I've always been a passive member, because I see my role mostly as a kind of a vector. I project the techniques that you develop, and I bring them to HPC, and in particularly now in the field of numerical weather prediction. So my talk will first, overview. My talk will first describe a bit what is numerical weather prediction, and we will look at the challenges we are facing now. As Bryce was saying, things are changing, and they are changing for very fundamental reasons that I need you to understand, to then realize why we take the decisions we take. We are going to take a little bit, travel to the past and learn a couple of lessons from some experiences at ECMWF in the past, and hopefully learn what we can do for the future. So, what is ECMWF? It's an international organization established in 1975. It has many European countries as member states, and they sponsor us, and we provide service to them. It's not part of the European Union. It is set aside, okay? So you have members like Turkey who are not part of the EU. What do we do? Every day we provide global weather forecasts, for the whole globe, okay? And they are medium range, so they go up to 15 days ahead. We also produce monthly and seasonal forecasts, and we also have a mission to collect and store meteorological data. We are based in Reading, United Kingdom, and we are about 260 staff, and lots of state-of-the-art supercomputers, and about budget of 50 million per year, half for supercomputers and half for staff. So that tells you that computing is a big deal for us. In a very broad picture, what do? We collect data about the world. We feed it to big machines. We crack that data, produce new data, and we disseminate that to our clients, which are the member states, and some commercial clients. I know that we have one client in our audience. We are actually forbidden to, by our charter, to deliver data to users, to end users. So we are basically a service and a data provider. So what is numerical weather prediction? We basically model the atmosphere. It's a very complex system, the atmosphere. It's actually not only the air. It's very important also to model the ocean, waves, for seasonal forecasts, the circulation of currents. The surface is very important also to model. If it's snowing, it reflects a lot the sunlight back up. Forests, for example, trap a lot of humidity, and so on and so on. So all this, parameterizations like clouds are extremely hard to do. These are very complex systems. And radiation, the sun plays a huge role in weather. And it's one of the heaviest parts of computation we have is the radiation part. And also, of course, the fluid dynamics, taking into account mountains like where we are now. at the moment is done in a subgrid scale. So it's not actually, we don't follow exactly the mountains. We say, well, there's a bit of something there. So all these parameterizations with time, we try to improve them. And that's our model. All this we code in usually partial differential equations, and we put them in the supercomputer, and we solve. But how do we do that? Every day, constantly, throughout the day, we take measurements, we receive measurements done by other people, data providers, from the state of the atmosphere. And we put that into what is called the data simulation. It's going to take a kind of a guess of what is the state of the atmosphere at that moment. And then that provides us our initial conditions. And then we start iterating and moving fast in time. Hopefully faster than actual time, right? Because you can have the best forecast in the world, but if it's late, it's useless, right? So, and then we have some intermediate results, which we call like raw products. Those usually are not in the state that our clients need. And then from there, we process that to send to our clients. And we also send and archive them, okay? Those results, so we run 2 forecasts per day, imagine. Well, now, actually, from yesterday, we started to run 4 per day. And I'm glad to say the change went okay, operational change went okay. Got an email this morning saying everything is okay. We take the steps, say that we computed at 00 UTC, and we correct it with the state of the atmosphere, of the measurements from the atmosphere that just arrived, and that is the initial condition for the next 12 o'clock or 6 o'clock run. And this goes on and on, always. So we keep updating our last best guess, okay? That's very important. So what are our sources of measurements? It's much more than you would ever think. Yes, everybody knows about weather balloons that go up. Did you know that aircrafts, when they fly, they actually send us data? And it's very useful data. Because it's taken at an altitude that rarely we have instruments there. And most importantly is satellites. It has been a huge revolution since we started having satellites that take pictures of the Earth and tell us things like where clouds are, right? Or they can measure wind everywhere. That was a big, big change. So we take around 300 million observations per day, and from 130 different sources, okay? So surface stations, polar satellites, geostationary satellites, aircraft, you see there the traces of the aircraft going, radio sound balloons, you name it. And we take all this data, and we can't use it all. It's too much. So there are very smart algorithms. Actually, don't work on that part, so I don't know them, but there are very smart algorithms to select the best type of data. And then we feed that into our model. We actually only take 20 million of them. Then we do what is called 4D VAR assimilation. So 4D VAR is because it's in 3D plus time. But in this picture, you just see 1D and time. So imagine you have the previous forecast, which is the blue one, and you now have new observations, which are the green dots. You're going to do a minimization problem, and actually this is very expensive, and in terms of computation. And then you're going to recompute a corrected forecast and say, oh, we missed something last time. Let's readjust new initial conditions, and then we go on. And this is done by a process of interpolation. So you take the points, F here blue, are where we had computed a forecast, the previous forecast, and then we have measurements, and we correlate both together to get a new initial condition, and that is in a grid around the world. Then we feed that to our model, and our model has to discretize, to split in little parcels the whole atmosphere. One of the ways we split it is vertically. So we take 137 slices of the atmosphere all the way up to 40 kilometers of altitude. That's very high, okay? Space starts about 80 to 100 kilometers. But so an aircraft is already flying way inside here. And we do that, and most of the slices are actually near the ground, because that's where interesting things happen. A meteorologist will also tell you that some interesting happen in the middle. But I'm not a meteorologist, by the way. And what we do then we also slice it horizontally. We do a grid around the world, and nowadays we have a grid with a resolution of 16 kilometers. So if you think about Aspen and this valley, it's bigger than that. So we don't have 2 points in Aspen, right? We may have a point over there and one over there. And for Aspen, to get the weather in Aspen, we interpolate. And because it's a valley, things are not exactly the same. Anyway, 16 kilometers is what we run in what was called the high resolution model, but we also have something we'll explain later, the ensemble model, and that's run in a 32 kilometer, usually half resolution, which actually means 4 times less points. That grid does have a big effect. This is the resolution we had before, or actually, no, this is the ensemble resolution, and you see that these are the Italian Alps, a bit smeared around. And this is with the current resolution of the 16 kilometers, and you see we can already spot where some mountains are. So horizontal resolution is also very important. It helps us define better the features that are happening in the atmosphere. And some features are very large, and some features are very small. So we have a scale problem. We put all that together, slicing vertically, slicing horizontally, and currently, at the current resolution, we have 2 million grid points horizontally, 137 levels. That means one variable, say temperature, around the world has 287 million doubles, right? That's just temperature. We need velocity, U and V, we need pressure, and we need humidity, and a little more. And these are, let's say, the ones that are everywhere, but then you have variables that only exist in the surface, and so on and so on. So it's a lot of data put into a supercomputer. And those operation models produce, after running, around 13 million fields, million solutions, if you want, raw products per day, totaling 14 terabytes per day. And all this, every time we run it, has to happen in 1 hour. From beginning to end, has to be in 1 hour, because we arrive the observations arrive, we have to process them, run the simulation, and send and be in our client's destination within a certain dissemination schedule. So it's a very, very tight schedule. And so to explain what was an ensemble, you know about chaos, and you know about the butterfly effect. You know that sometimes the weather is rather easy to predict. And sometimes it's not, because a lot of things are happening. So what we do, instead of running just one forecast, in that space of 1 hour, we actually run 52. We run a high resolution forecast, and we run 51 lower resolution forecasts, which was what we call the ensembles, but all of them slightly perturbed here and there. And the way we perturb, again, has to be in a smart way, so that we cannot be too much perturbed, else it's unrealistic, but it should be perturbed in a way that we cover all the possible variations. And so sometimes as time is, we are comparing with what actually happened, okay, which is the dark blue, with what we predicted that day, and we see that sometimes we get that the interval, which grows obviously with time, because errors accumulate, sometimes we get a forecast, well, it's not too bad. But sometimes the 52 members are all over the place, you know? And that means that we were only doing a forecast that was good enough for 2 days. And these are, for example, the 52 members, in this case, predicting pressure around the UK. And you see they are, in this case, they are very, very different from each other. In the end, when we produce all this data, we still have to process it for our users. And we do that by running what was called product generation. It actually happens in parallel with the other one, with the run of the forecast. So whenever a step is ready, we start post-processing it. And we post-process around 77 million products per day, totaling 6 terabytes. And then we send this to the clients. And these are actually user-derived requirements. So they send us how they want the products, okay? And we incorporate that. They send us the previous day, we incorporate that into our system, and then the next day they have the new products, okay? So here the scope for optimization is not too much. And then we have a special dedicated network just for disseminating meteorological products around the world. And these are the points where we, okay? And then, so, just for you to have an idea, we don't only send the data, we also have some web services. So, if I can show you, okay, you can see that, yes. So, this is Aspen, and this is the weather for the next week. And say that tomorrow, there seems that there won't be so much rain. But over there, with actually a bit of an error bar, we were not very confident about that, but tomorrow it might rain. Okay? That's precipitation, by the way. And actually, if you look at the temperature, they will be around 0. So down here, the graph that is not showing, it actually says it might snow. Over there, Friday. Yeah? But the error bar is big, so. I mean, when I flew in, Candler was helping me in the airport. Thank you, Candler. I told him, the next week is going to be fantastic. It was sunny all the time, you know. We got correctly the snowstorm that trapped us in Denver, but we totally missed this forecast. So it was, you probably were in one of those situations where the butterfly flapped the wrong way and we just got it wrong. Happens. Fortunately, not a lot of times. Okay, so challenges ahead. There are 3 challenges we are facing ahead, and I will try to explain them separately. I call them scalable algorithms, platform uncertainty, and big data. So what I mean by that, we need, it's a must, we need to keep improving our models. We need high resolution, better assimilation of the observations, more modeling of more complex physical phenomena. Clouds, for example, are very badly forecasted nowadays. The model is crude, but it's very expensive to make it better. So we need more processing power, or we need to do it smarter. And we need to add more ensemble members because that helps us compute our errors. We need more computations, but that must happen within 1 hour. And over the last decades, so that starts 1881, our forecast has continually increased in quality, in score. So this is there is an international scoring system, and you see that nowadays we compute with a rather very high confidence. This is percentage, so let's say call it percentage of confidence, almost 100% over a D+3, so 3 days in advance. That's quite good. Nowadays, 5 days in advance, we do it 90%. It's a very good forecast. And it's interesting to see that the top line and the bottom line, it's the different hemispheres. Northern hemisphere used to be better forecasted than the southern hemisphere because there were no observations in the southern hemisphere. Now, with the advent of satellites, we know what's happening in the big space that nobody lives there, like South Pacific, and now we can forecast better. So that is improving, but we need more. And I want now to do a little game with you. See if everybody is awake. Yes?
Don't you feel that vertical scale is a little misleading over there?
If the vertical scale is a misleading in terms of?
Well, the distance between 80 and 90 is the same as between 90 and 95.
Yeah, it's probably stretched. Yeah, because the closer you get to 90, oh yes, repeat the question. Yes, the scale is a bit misleading. Yes, it's not linear scale, agree. Because as you get closer to 90, it gets harder and harder to advance. So you kind of have to stretch the scale to see any change at all, right? Yes?
Is there some kind of like technological advance or between 1999
Yes, you were asking if what is causing this big advance here around this period, isn't it?
Yeah.
Yeah, it's because that was, if I understand correctly, it was the introduction of satellites. Okay, when we started getting better and better observations. Okay. So I want to do a little game with you, for you to understand how the improvements in the forecast are important, okay? I'm going to show you a series of pictures, and when you know what the picture actually is, you raise your hand, and you try to guess, okay? So in 1980s, we had a resolution of 210 kilometers, and if I would use that to represent what I want to represent, it will look like that. Can you guess? Well, some years later, 125 kilometers resolution. Can you guess? Sorry? 63 kilometers? Yes, you want to take a chance? Come on. 39. Starts to get easy now. It is a hurricane. 25. 16, what we do today. And notice, when did the eye of the hurricane start appearing? An actual hurricane, the actual picture is that. That's where we want to be. Because that eye of the hurricane is very important. It has a huge depression over there. And that's home for you, right? Hurricane Sandy. We got this one right, fortunately. But we could have done even better. If we then took the data that we used for the Hurricane Sandy simulation, and we used an even better model on that, of course not in 1 hour, and we could have predicted even better where Sandy would have hit. And if we would have done it with a lower resolution, not the higher resolution we have, like the same resolution we had 10 years ago, Sandy we would have predicted the wrong time of arrival of Sandy. So this is very important. I mean, there is an incalculable number of lives saved in New York and New Jersey just with this simulation. Okay? We warned the US 5 days in advance. Yes?
Can you just run a localized model of higher resolution?
Yes, you can. We don't. It's not our task. But that's what the national services do. So the question was, can we run a high resolution in a local area? Yes, you can. And that's what our clients usually do with our data. They use our data as boundary conditions. Okay? So increasing resolution is very important. We are here nowadays, and we are planned by the end of the year to arrive to 9 kilometers. And this is how heavy it gets. With the years, we are expecting to arrive to a resolution of 5 kilometers. And this is the size in memory of each field, of one field, one slice of the atmosphere, one variable. It nowadays is this, 16 megabyte. It will be 67 at the end of the year. in where we want to be in 2020, 25, it will be 160 megabytes for one variable. So something, and if you think that GPUs are getting lower and lower in memory per CPU, that's a big problem for us, especially for the data processing part, because the data processing has to do some interpolation on the whole data. Big challenge there. There's another big challenge ahead, is power. So our forecast actually only uses 2.5% of the supercomputer when it's running. Well, it uses 10% for operationals, okay, which is, so 25% are used for operations, of which 10% are used for the global forecast, okay? So 2.5 is the high resolution forecast only, okay? And if you scale to the resolution where we want to be in 2025, with the current machine, with the current technology, we would need 2 megawatt of power. And that means that the whole supercomputer would be using 60 megawatt of power. So now something has to change, because we can't go on like this. So platforms are moving ahead. We are getting new platforms, GPUs, lower power, but that is also introducing a very big uncertainty, because actually right now nobody knows what is going to be the real next big winner. There is so many, I will show you, the landscape is a bit heterogeneous at the moment, and we don't know how to best use them. It looks like we have to rewrite a lot of code. So, and we have very limited resources because they are not increasing our budget. Okay, the number of people is going to remain the same. So at the moment, there's a big proliferation of architectures. The usual suspects, Power and Intel. We used to have Power, now we run with Intel. Then new GPUs. Many people are switching to using GPUs. Our model, it depends which algorithm you have. There are algorithms that scale very well in GPUs, but ours apparently doesn't. So we are kind of waiting a bit more for that, for the Intel Phi. The previous generation was so-so. Apparently the new generation, very promising. And NEC is looking into something very esoteric, and we are waiting to see what comes out of that. But there are even newer kids on the block. There's a whole now interest in ARM. Oh, why is that? I think your company has something to do with that, huh? Well, ARM actually has a big advantage, because these CPUs consume very little power. And you can see that in this graph. That's actually for the last one, for this one here. So that's two standard CPUs, the same actually, but loaded differently. One single thread, hyper-threading and oversubscription. And here we have the Intel Phi. So this is performance, that's power. And you have the Intel Phi, you know, the more you pull out of it, the more power it needs. That's normal, but asking quite a lot of more power. And if you run one of those little guys, yes, you get less power, right? They are not as powerful. But you get what? A third of the power of an Intel Phi at maximum, at peak? But what? A fifth, a sixth of the power consumption? That's a game changer. So this is a prototype CPU, huh? This is just a test. It is not yet on the market, but if they manage to pull it, that's going to be very interesting. But so how are we going to change our software stack to deal with this? We come in, the developers. Need flexibility, need performance, a code easier to maintain than Fortran, a modern language. I have the solution, or we have the solution, C++. But if it would all be so easy. We have quite some restrictions, some technical, some economical for our HPC platform. It has to be POSIX, that's okay. The only supported languages at the moment in the contract are Fortran, C99, finally C++, because some years ago there was not even the mention of C++, but certainly not C++11, Shell, K-Shell, Perl, not Python. And most of our scientists actually know is Fortran. Maybe some know Python. And some basic shell scripting. So we need to put this into the picture. So 4 years ago when I joined, yeah, C++. Now I'm like, oh, how am I going to do that? So the C++ support on the HPC is a bit patchy. Some compilers don't fully support C++ 98, okay? And I'm not going to name them, but for example, Eigen, which is very used for linear algebra, cannot be compiled with a certain compiler. Parts of Boost, serialization, Proto is a no-no. Also, they give up immediately when it's Proto. Not to mention C++ 11. I mean, some things of C++ 11 they give you shared pointer. That's good. But other stuff like lambdas. Anyway, but there is change on the way. Some meetings ago, they asked you, are you interested in C++? Yes. So they are starting to warm up to the idea. And I think it's because all around the world, people are asking for it. Communities are asking for it. People are realizing that maintaining 2 million lines of Fortran code is very hard. And something has to give, right? But scientists are very reluctant to use C++, okay? And I have my view on this, and I will try to share with you. I think, and if somebody is here from the committee, maybe they should take some things into account. Fortran is what they know, okay? It's very fast for numerical algorithms. And at the beginning of C++, I mean the end of the 90s, C++ got a lot of bad rep. People said, it's slow. They didn't know how to use it. They took their Fortran code and rewrote it in C++. And then whenever they had a Fortran vector, they used std vector, right? And yeah, guess what? You know, if you copy the vector all the time, like Fortran doesn't, but if you are, if you don't know what you're doing, you are copying the vector a lot of times, right? And you don't know. And you write the loops as in Fortran, right? And in C, we put things like this, and Fortran puts things like that, and then suddenly all cache misses, and the loop runs 4 times slower. And then they don't know about the restrict keyword, right? If you don't know about the restrict keyword, go and read about it. It's very important for performance. But that got corrected. The community, Todd Vildusen, Andrew Lumsdain, Professor Langtangen, Simulabs, they all did a lot of pioneering work showing that you can do good software and you can do fast numerical code with C++. But still, C++ is seen as complex, and I think templates are usually the common complaint, okay? People look at templates, all those, and they go like, it's like, what is happening here? I don't understand this. And, okay, you could say, yeah, let's hide that. But another thing is this is more like from a management point of view. Is it as portable as Fortran? Is it as portable as C? And until the vendor, it's kind of a chicken egg problem, right? Until the vendors support it wildly, okay, we have a problem with that. And as the language keeps changing, and I fully support that the language keeps evolving, but now we have things that are compiled with C++, that only compile with C++ 11. I can't use them. LLVM, would love to use it, right? But you can't, because there's already C++ 11 there. So, okay, I will now speak about the next challenge, and I'll try to be quick, because I want to show you some code, and you're probably almost asleep. At TCMWF, I believe we have a big data challenge, okay? Big data was defined in 2001 by being something, data that has high volume, high velocity, and high variety. 3 of them, okay? So let's see if we have big data at ECMWF. It's called the 3 V's of big data, by the way. Volume. We have exponential growth of assimilated and received observations. That's the jump that, by the way, you were asking about. The increase of the skill around the 2000s came with the increase of the satellite data. And you see it here. The generation of products has also increased, not really exponential, but quite fast, and also in variety at the same time. These are all in millions, by the way. No, this is, okay. This is 1 million, okay? Here. 1, 2. And this is our archive. That's where it gets interesting. This is our archive since, you can't read it, I can't read it too. I think that's since the 80s, okay? Our archive has exponential growth rate, okay? That was an exercise to delete 1 petabyte of data. Took our researchers 6 months of work. Okay? So during 6 months, researchers really looked at their experiments and at their data and say, oh, should I keep this? Should I not keep this? And they had a web-based app where they selected their apps and their experiments and deleted them. That's the effort. It's not effort. It's pointless, you know? It's really pointless. And the reason why is explained here, is velocity. Because if you have exponential growth, and you remember a little bit of your maths, you derive the exponent with respect to time, and get what you get back? An exponent. So exponential growth means exponential rate of growth, right? That's this. So we archive nowadays 100 terabytes per day, okay? At the end of the conference, more or less 1 petabyte more in our archive. So I stopped counting. When I joined the center 4 years ago, it was 40 petabytes. It's already in the 80 petabytes, okay? So it doubled just in the time that I was there. Variety. We have also a lot of variety in terms of what we do, what we generate. This is a logarithmic scale, by the way. So as time has passed over the decades, from 85 to, this actually only goes to 2010, we have done more with our data. These are all different events. We started doing different things. That's why it's kind of a scatter plot. But the idea is that the rate of has grown correlated with the variety also. And that's the reason I want to show you that only 1/3 of the growth of the archive is coming from the resolution increase, bigger data. 2/3 is coming from more data, more diverse data, because scientists are doing more science. And that means different types of variables, different types of data. But nothing of this is new, because we have exponential growth since 20, 25 years. So what is changing? Why am I worried now? You all know this graph, yeah? Herb Sutter, famous article, no free lunch, or free lunch is over. So we are stagnating the megahertz of the processor, right? But what about the real performance? Are we also stagnating? It's a different graph. This is single-threaded performance. We are not really stagnating. We are still increasing, but not at the same rate. We have more registers, we have vector units, branch prediction, but it's also harder to obtain. To squeeze up those extra flops there, it's a lot of hard work. Because you have deeper memory hierarchies, out-of-order execution, compiler doing things that you don't expect. You should be vectorizing. Why aren't you not vectorizing? And then you find out there is a restrict missing somewhere. That's CPU. But storage is a slightly different situation. In terms of storing volume, right, capacity, we are not stagnating. Many people during many years said that tapes were going to die. Not really. This is an IBM article from 2011. Tapes are still growing quite well. Other technologies, disks, etc. We're getting there. I mean, now with flash and non-volatile RAM, I mean, it's okay. We can store things. But how about the rest? This, by the way, is another article. That plot was the blue plot of the other one. That's the growth again. But what about the I/O rate? That is stagnating. Over many years, we had increased I/O rates, but since the 2000s, your disk is not transferring much more. So we are creating a bottleneck there. So we all know about RAM bottlenecks, right? But I/O bottleneck, oh, that's becoming harder and harder. And just for you the biggest supercomputer in the US is going to have an upgrade. They are upgrading everything. CPUs, number of cores, memory. The only thing that is not upgrading is the I/O rate. Because it's simply, I think, technology. I don't have a real explanation, but I think the technology is simply not there. So that means that we may have the capacity to store things, but we might not have the bandwidth. So now wrapping up all the challenges, what does all this imply? That, okay, for the NWP community, we had paid for the lunch a long time ago. Okay? Our codes have been parallel and concurrent since the 90s. Okay? So there was nothing to be done there. But what has not been done is look at optimization for data movement. We thought data movement was cheap. Let's load some terabytes from the disk. Let's write some terabytes from the disk. And all this, nowadays, the supercomputer spends a lot of time waiting for I/O. Okay, so we need to optimize for data movement. And if I may say so, I don't think we are the only community needing that. We need to develop also new algorithms to go with that explore data locality. We have to explore more concurrency, not at the level of the software, but at the level of our algorithms. Can we maybe do things slower, but more at the same time? And also, hopefully, introduce some flexibility in the code, because we don't know what is the platform coming, so we have to be prepared for it. So all this brings us to how can we tackle it? And I want to take a bit of a step back into the past and tell you a little story. I joined ECMWF 4 years ago, and I had the fortune to join what's called the Mars team. Okay, so Mars was originally made, developed, maintained by these two people. Baudouin Raoul, nowadays he is our software architect. He should be here talking, honestly. He knows much more than me. And Manuel Fontes. And when I joined, I had the privilege to join their team. This is Mars, the Meteorological Archival and Retrieval System. It's a managed archive. It's not a file system, okay? Users are not aware of the location of the data. They just send blobs of data there, we index them, we store them, they can retrieve them whenever they want. When they access it, or when they specify operations on it, they do it in meteorological terms, things that they understand. And the data is kept forever. You have seen is pointless exercise deleting data. And the more we accumulate data, the more our data set is rich. The more you can do things, data analytics with it. And it consists about 3 layers. One is a kind of a cache directly at the supercomputer with a 80% hit ratio. Another servers with spinning disks, again 80% hit ratio, and only 4% of the time do we go to actual tape. So it's quite efficient if you think about it. Nowadays, it's a fully distributed service, 15 servers running, it's not many in my opinion, serves an 80 petabyte data archive. You can access everything on the archive. There's nothing like locked that you cannot say, oh, no, you don't go there because this would be too slow. You can access everything, okay? And a percentage of caching for that is quite low. It's around 1.5 petabyte for just 2.5% of cache. Cache space that we have to use, that we can use. We have very big numbers of files, of fields. We data collocate a lot, so the index that we generate is very, very, very small compared with the amount of data, okay? The index is in the order of few terabytes for 80 petabytes of data. And many, many billions of entries in that field. There's a lot of compression of the index itself. 100 terabytes added daily, 100 terabytes retrieved daily. 2 million requests more or less per day. Fully written in C++, starting in 95. So this is before the standard, okay? And its index is an object-oriented database. And if you know about databases, getting object-oriented databases running is not trivial. And its file, it's persistent. The database is persistent in disk all the time. When I joined, it actually was a monolithic server. It was running in AEX. It had a metadata that was indexing 40 petabytes, and they were in a job of 2 years for planning to migrate this to fully distributed, running in Linux, changing from big Indian to little Indian. And I joined, and I sat down, and I saw these two engineers working, and I was learning still. And in one morning, I mean, with few hours, with a degraded system only, there was no disruption, okay? There was only a degraded system. We did the whole migration. I was gobsmacked. How is this possible? Because of this. There is when users access this, when users access Mars, they use it via a language that describes what they want to do. It has, and it's parameters, it's things that they understand. They know what is temperature, they know what is a forecast, they know what is pressure levels. You don't, but they know, okay? This simple request here actually identifies nearly 5,000 fields, including interpolation. So it's a very concise way, and it's the way they talk to the system. So there is an indirection in the middle. And that's what I learned that day. Sorry. Indirection is the key to scalability. Think about this. Indirection is the key to scalability. Usually we think about indirection like abstractions, okay? Yes, I would actually say a good indirection is an abstraction. But you can have indirections without abstractions. And usually people say, oh, virtual functions and performance, they don't go hand in hand. And, you know, I've been doing HPC for a long time, and the price of a virtual call is really small compared with what you're going to do in hardcore number crunching. So don't start templatizing the code because you want to save a virtual call, okay? You will be harder to understand the code, and your scientists will defect you, you know. So, has happened to me. So, this is a very valuable lesson. We are going to use it now, okay? So now we are going to finally see some code in C++. So we have two projects running now at the ECMWF, looking into the future, tackling the scalability. One is called Atlas, one is called Hermes. Yes, we like Greek names. The aim is to tackle the big data challenge, introduce an adaptable solution with flexibility, okay? And hope that this has maintainability for the future. Let's use C++. 98. So, Atlas. So Atlas is done mostly by Willem de Koning. I help a bit. And is hoping to face the challenge of new algorithms and platform uncertainty. And the current model, this is the IFS, the crown jewels of ECMWF, is 2 million lines of code, 9,000 routines and modules in Fortran, hybrid MPI, OpenMP, fixed data structure, quite well organized, honestly, but lots of global data. And it's totally impractical to think of rewriting it, okay? Don't even go there. There's a lot of thought and physics and scientist code that they don't want to change it, okay? So we need to change something else. Fortunately, there is what is called a dynamical core, which is something that does the fluid dynamics of the whole world and the whole globe, and that is underlying and in a very located part of the code. And that's what we are going to look at. So Atlas is a framework for a parallel dynamic data structure supporting multiple types of grids, fully written in C++, providing Fortran 2003 interfaces, and it's a basis for a scalable dynamical core. Something we will want to change maybe in the future, but we are putting that in direction there, and yes, it's an abstraction, that separates the Fortran code, the numerics part, from the data management, okay? So it does already things like the parallelization of the whole data structure, the communication with MPI, the distribution with OpenMP, and even computes the overlappings between, the communication overlappings between the domains. So it's shaping up. How do we do that? So we keep the Fortran for the numerical algorithms, and we use C++ for all the data and memory management and message passing. For every C++ class that we want,
How are you representing your grid? Are you doing something like cube sphere or thin shell?
So the question is, how do we represent the grid? And if you are from the field, you know there are many, many ways of representing the grid. This data structure is agnostic. You can represent any grid in this data structure, including unstructured. So we use then Fortran's ISO-C bindings, which is recently on the standard of 2003, added a way of cleanly interfacing Fortran with C, no more decorators, underscore, underscore, and things like that. And so we created every Fortran object that we want, every C++ object that we want to have access in a Fortran. We provide a Fortran object, which is methods with only methods, that delegates via Fortran to C bindings through a to C interface to C++, whatever we want to do. That's the way. I wish we would have a better way. There's a lot of auto-generation of code here. Things that I wish a compiler could do for me, honestly. The C++ contains the implementation. So no fancy C++ here, I'm sorry. You have here a field, has some data, and what we build is a C interface that where we pass this, right? And actually this here should be capital T, because else it doesn't compile in C++, right? But we pass this, and then we can forward that call to the C++, right, from the C. I'm sorry, I have to. Oh, sorry. So then what do? We have a Fortran type that is only functions, has their C pointer, which then gets properly set in a gluing code that is actually Fortran calling the C interface, okay? And that's the function call that you saw back there. You notice that there are no decorators here, so the ISO-C bindings does the correct thing. And then we use a special ISO-C binding to transform a C pointer to a Fortran pointer. And yes, for those who didn't know, yes, Fortran now has pointers. So, and then you got that. The outcome of this is a Fortran program that almost looks like C++. Look, you have a class field with a % operator, which is our dot or our arrow, okay? Calling a method with a parameter. It almost, it looks so much like C++ that we actually provide another layer on top so that the scientist doesn't have to learn object orientation. Okay? Anyway, that was Atlas. Now Hermes. still have, yeah, I have enough time. So Hermes was another project that we started, me, Baudin Raoul, the software architect, and Florian Ratgeber, who joined us recently. And we want to address the big data and the platform uncertainty with this project. So what is Hermes? Let's have a look at the data chain. What do we do with our data? We take observations, we put them in some database, then when it's time to process, we pass them through different filters and different processing units. It's very abstract here because I don't want to go into the details, and some more of them, and then we put them back into another database, and then we have actually the ones that we want to use in the way we want to use them, and then we feed them to our model, to the IFS. That's the observations part, before the model. After, the model produces the raw output. We put them again into some file system. For generating the products, we do some post-processing, interpolation, cropping, some more processing, and we write them to another database, the final products, which then are sent to dissemination into that global network, and that's it. So, two data chains, but they have some similarities. I think you spotted the pattern, right? So both are processed in pipelines. Both are parallel, concurrent threads or OpenMP, distributed, possibly with an MPI. But how do they differ from the actual model where we do the hardcore computation? I mean, the model is parallel, but needs synchronization every time step. And here, there is little or no synchronization. There's no time evolution. And this is what people usually call the embarrassingly parallel paradigm, okay? Nearly. There are some exceptions there, but. So that makes that we can do some possible automatic parallelization. So to do that, what we would require is some way of defining computations, some way of efficiently performing them, accepting data and delivering results, flexibility for maybe future architectures that we don't know even about now, and set in such a way that is understandable and extendable by scientists. So, solution? Indirection is the key to scalability. We are going to decouple what we want to compute from how and where, okay? And what I'm about to present is maybe obvious to you, but this in our community is not, okay? So again, we are trying to bring things from other communities into the NWP community and use them. So we are going to have some user requests. We're going to generate some tasks that we are going to perform, and then we are going to dispatch them to different places. This is basically a front end with multiple backends. And what we need in the middle? A language, okay? So we are going to have a language for computations, okay? This is not like full feature language that you want to program everything in, okay? This is just to define computations. And if you know a little bit of functional programming, that's what we got our inspiration from, okay? Again, observations come in, we process different pipelines, then we're going to dispatch them to different places, but we're going to have a front end and a back end, and we're going to express those computations with that language. And note here, we are going to reuse some components, and we are going to compose them, okay? So mathematic notation there, age of G of F, right? In the future, I would like that a scientist that needs to look at data, and the data is so heavy, that is on the order of many gigabytes and terabytes and petabytes and whatever, he doesn't have to actually touch that data, okay? We dispatch the computation to an interpolation, say, cluster, and we get back a reduced set of data, or even the image itself that he wants to see. And if, again, we just need a front end, a back end, and some language to describe what this computation has to do. So that's what Hermes is bringing. is a DSL for defining computations, a front end to send those requests, a broker to dispatch the work to processing units, and multiple computational backends. At the moment, we have CPU, CUDA, and MKL. We are still in a prototype phase. We are looking into using Intel TBB and HPX. And I'm really impressed with HPX. Unfortunately, I can't use HPX for the whole thing because I find that it's too low level. But it's really useful to make a backend on. So that's what we are going to use it for. We have, this is very common for you. This slide I use more for scientists, for them to understand what actually is happening. It's a broker in the middle with a message queue, a picker, handler, dispatching to consumers. There's nothing new there. So we have an expression engine. So it's a prototype, domain-specific embedded language in C++. So it's fully C++, no parsers, no, you use the compiler to compile what you want to do and you send it. We will support plugins in Fortran. We know how to do it. Actually, we are going to do it the way we do it with Atlas. We're going to bring that here, but we're going to flip it upside down. So we are going now, C++ is going to call Fortran. And we have expressions as trees. Expressions are trees and a hierarchy of expressions, right? With terminals and functions. Terminals with value semantics. Functions are pure operations. This is very much inspired in Haskell. Expressions are immutable. Functions are pure. There are no variables. They're only constants. It's lazy evaluation. And we put in an optimizer inside that looks at the expression, does some pattern matching, very simple, honestly, and then can do some collapsing of expressions that are easy to collapse, or detect common sub-expressions, or something we haven't done yet, the automatic parallelization. We're still in the inception phase, so actually would like some feedback. So that's the expression class. Everything we move around are shared pointers. Once we create an expression, we never change it again. You'll notice that all the methods are const, except for except for. I wonder if that should be const there actually. I copied it from the source code. Okay, this is not something that compiles obviously. So, what is an expression? It has an eval. An eval always tries to optimize first, and then call evaluate. And evaluate is the virtual function that actually does the evaluation. By definition, we also can optimize, but the default optimization is return yourself. I don't know what to optimize. So concrete types can know their optimization. Okay. We also have something called resolve. And resolve is for parts of the expression that not yet complete, okay? So they are parameters, say, for example, in a lambda, okay? So we need to always try to resolve unresolved things when we are collapsing and returning the result, right? So that is the interface. So values are, for example, the values, of course, are expressions. A value is an expression that evaluates to itself, always. And then we have many different types of values. This is an example for the real. It just has the methods to return what he's wrapping, the value that he's wrapping, okay? And crucially, every class has what we call the signature, which is then we compose signatures, and that is what we use for pattern matching, okay? So because this is in a way dynamic, everything is always expressions. But when you ask for the signature, you are in a way asking for its value, okay? For its concrete type. It is not really the concrete type, okay? It doesn't use dynamic cast here, okay? It's really for tell me when you get evaluated, what type are you, right? So, and I use this to pattern match and for dispatching to the best performing backend, for example. values are like bool, integer, real, string, list, vector, matrix. What we need. I mean, in this language, we are only implementing things we need, okay? It's not like fully Haskell, okay? But we did some implementation, you know, to try to see if it was a sound language. I'll show you later. Functions are obviously things that evaluate some computation, and their signatures are composed by what they are plus their arguments, okay? So the signature returns something like the name of the function, plus the things that are actually sitting inside, right? So I can now pattern match on this. Itself, the class function has the dispatcher there, so I can register to this dispatcher for a certain signature what executes that signature. And I'll show you later how we use that. Okay. For example, oh no, here we are still in function evaluation. So when we evaluate, we take all the arguments that we have, and we have to make temporaries of them, obviously. We don't want to change the current ones we have. And we ask the arguments to evaluate themselves. So you collapse, basically. It's the depth first, right? And after that, we can compute the new signature, because there may be some arguments at that time that was not yet fully resolved, so we need to collapse those. And then we can dispatch, and dispatch is really just a map to a function, to a caller, okay? And since everything here takes exp, it's a very, very simple call, right? It's just exp with at least a vector of exps. And we dispatch that. We also have an optimizer. So when the optimizer fails on itself, on a class that with a virtual call, we can still, at the level of the function, dispatch to an optimizer that looks at the tree as a whole, okay? Okay, for example, map. Map is a function, and it takes two arguments. One, the function you want to map. Two, the list you want to map it to. And what we do, we go through the values, we extract the list, we loop over the list, we always resolve, because the members of the list may be expressions themselves. It's not like in Haskell that the list has to contain all the types that all have to be all the same. Here the list can contain any more expressions, okay? So you collapse that list also, that expression also. In the end, you end up with finally a list. And then you use that, and you return the new list with the results. Just an example. We implemented many different functions. Most of these functions we implemented actually was more to stress test the engine of the language, see if it's really sound. Now we start to do some computations, but I'll show you that. So real examples, this is C++, this compiles, I can show you the code. Here you'll see some C++ 11. We have been allowed. Okay, so you create a real, we create some vectors, we do an add, but if you print what that add is, it's the expression, it's not the value, right? The add is an expression. And then we can put that expression into another expression, more complicated. Then we can evaluate that expression to itself and assign it back to itself. So here, this is just the pointer we assigned. We didn't change the expression, okay? It was just a pointer got assigned to another expression, okay? And the other one got deleted. Or did not. Because I put that C over there. So if I now print star C, it does show me something that was evaluated fully, so it's real 6, the addition of those two numbers. But if I now print what is E, E still has the original C expression inside, because it's immutable, right? I put it inside, it stays there. And then I can, of course, optimize E to get this maybe more compressed. Interesting. The optimization of E turns out that this is called a linear RV-RV. Because it's a linear combination of vectors. So scalar times vector times plus scalar times vector. So we pattern match this thing here to be this. And I know how to execute this on a GPU very fast. There's a call in Plus for that. So that's what we're looking for, is optimization of things that are recursive in what the scientists do. They don't realize it, that they're actually doing a BLAS call. They probably even usually code it themselves. And then we are going to dispatch it correctly. And we can do other things like reduce of a lists and things like that. A bit more complex. Lambdas, we implemented lambdas. So in this case, a lambda is called twice. It does 2x. And I can have a list, and then I can map twice to the list, and I have a list of the 2 times that what I had there. So nothing very special here. But what we can do also is currying, and that took a bit more of work to do. So you compose, for example, 2 lambdas, one inside the other, and you define ij, and then you can curry. And you can define h is basically uses the f curried with 2. Thank you. And then we can apply again another curry, another one, and finally have something that is fully closed and have a g, which can now be evaluated to real. By the way, you may have noticed that I introduced expr. Capital expr is a class that's just a wrapper around expression pointer, and it provides value semantics and convenience operators, star, and things like that. So it's just a convenience for syntactic sugar. You know what a Y combinator is? So Y combinator is basically a function that allows you to implement recursion when your language does not support recursion. Okay? So we said to ourselves, if the languages can do a Y combinator, we are on a good track. Let's try to do the Y combinator. It took a bit of refactoring to do, but we got it there. So Y combinator is defined there. It's f of the call of f applied to f. And we have here a Fibonacci implementation with a lookup table, by the way. It's more efficient. And we define it also with a couple of lambdas. And an if else, because if it's in the lookup table, we do not need to go and compute it. So we take from the lookup table or we compute if it's bigger than 10. But you notice that here in this Fibonacci, this not complete yet Fibonacci function, there is no call to himself. Fib does not call himself. But I define Fibonacci as applying the Y combinator to fib. So the Y combinator is going to make this a recursive function now. And then I can call Fibonacci of 20, and it computes the Fibonacci number. Okay? I'm going to go quickly through these slides. This is slides I use to show scientists that we are doing a good job in optimization. You know what this is? This is basically constant optimization, folding of constants. We have that implemented, obviously. Filter, you can have a filter expression, and at optimization time, we can apply that filter to the list and filter, and therefore we will not apply the computation to all the elements of the list, only the ones that pass the filter. Future work, we will look into map fusions and composition, and the aim, the final goal is doing this, is to be able to express our computation with a list of many, many fields that we need, for example, to interpolate and maybe perform an average of all those fields and send them over to the supercomputer. And the supercomputer will change that, optimize it, and say, oh, I have this amount of nodes available. I'm going to spread that work through the nodes automatically, and then I will reduce that, perform the average, and return to you the result. Okay? But this will be done automatically. That's what we want to do. You know, the scientists should not know about this, that is happening, right? Nowadays they do. Nowadays they implement these things. Few of them. Okay? And we also implemented linear algebra functions, vector-vector, matrix-matrix multiplications, optimizations. And we have different backends to dispatch to. For example, we have at the moment, we have only the basic operations like vector, vector, matrix, vector, vector. All those then can be dispatched to GPU, to say the MKL library in the case of the Intel, because that's what we are currently, our current platform. Or even if where we are running doesn't have any of them, we have a generic engine where we try to do our best. So that's how the client code looks like. I can send some expressions and it gets executed remotely. And that's how the engine looks like. So for every implementation, say, of a function, this, for example, implements, what is that? The generic dot between two vectors, and then we have to register it to the function dispatcher like this. It's just a function pointer. And then, say the MKL implementation, or the GPU implementation, with all the CUDA calls inside, all register themselves. So, nearly done. I'm going to attend a live demo, right? And as you all know, live demos have a tendency to go wrong, right? So, yeah. Did it go wrong already? Yeah, it did. Okay. Give me a second. So I want to do cross-continental computation. Okay. Oh, you're going to win bear. Yeah, okay. That's fine. No, I want the other one. No, sorry. I did the other one. Uh-oh. No, this is what I want. Apple, the new force feedback touchpad is a bit confusing. Yeah, here we are. But I love Apple, huh? Okay, sorry. We are very security sensitive in my place, so have to make a very special SSH tunnel. Are we in? Yeah. Okay. I cannot really see what I have, but no. Build Hermes bin. And now, yes. Let's start our server there. So we have a server waiting for computations in Reading, United Kingdom. It has a GPU backend, it has a CPU backend, and it has an MKL backend. And over here, I'm going to send some expressions for him to compute, okay? From my laptop. I have another terminal, I could show you another terminal, but you'll probably, do you see that? No, not really. Anyway, there's not much to show. I type, basically a local port here is going to send it there. And you should see, okay, he accepted some requests and he's computed some simple requests like vector operations, but he is busy now with the matrix, a quite big matrix multiplication. It's going to take about 30 seconds, and he's going to say, okay, I'm done. This is because it's the generic CPU code, okay? And that's exactly what we want to, if I would be doing this computation right now in my laptop, I would be taking roughly the same time, because the CPU is roughly the same. It probably even took more. So now you get the result, okay? And I'm not going to print the result because it's a very big matrix, okay? But it's 1 million entries, but you see there that the result is there, Okay, took how many seconds? Took should print out the time it took. Should be around somewhere. Did I comment out the? It should print. Anyway, but now I'm going to select the GPU backend. Well, it's called CUDA, and hopefully, if everything goes well. It's taking its time, actually. Oh, no, it didn't. Yeah, this is threaded, right? So, 1, 2 results, 3 results. Where is it? Should be there. Let's try that. Oh, no, okay, sorry. I misspelled it. It was still the CPU because I misspelled it. So this is CUDA. Okay, ready? You see? The CUDA matrix got even first than the vector one, because this is all 4 threads working at the same time, okay? So, and the MKL is not too different. There you are. So the matrix is over there in the bottom. So you see, all this is what we are aiming at. We're still in the inception phase. We are not yet there. We want to use real data. Now it's fabricated data. We want to use meteorological data. But it's a 3-year project. Hopefully by the end we'll have an operational system that can do this for our clients. And I now have some time for questions.
So if people have questions, if you can just line up here.
Oh yes, please line up for that. Everybody asleep?
Yeah.
So my question is concerns that what you said about impossibility of rewriting the big Fortran global circulation codes. And I would like to ask you to elaborate a bit more, and maybe I will say something provocative. That don't you think that it's a bit like with space shuttles, that at some point they will become too expensive to maintain? The millions of Fortran codes, lines of code.
It's funny you asked that. I'm an aerospace engineer by training. The two industries are very different, I think. They are both very conservative, very much. But, you know, the sheer size of difference in budgets is amazing. Honestly, it's not because I work in meteorology, because I used to work most of my career in aerospace. But meteorology is seriously underfunded. For the bang to the buck that we give, the amount of lives that meteorology, a good meteorology forecast gives, I think it deserved a bit more investment, okay? Now the UK, for example, has woken up for that. The government of the UK has given a special budget of more than £100 million to the UK Met Office to rebuild a whole new site for the supercomputer to host what is going to be one of the biggest supercomputers in Europe, just for meteorology. So, and they realize that this costs money. They thought just about Heathrow, okay? Heathrow Airport, a morning with fog. The costs for the economy that all those delayed flights causes is a huge amount of money. So if we can do what is called, what you were asking, a local forecast for fog in London, and be sure that, the fog by 9 o'clock is going to be cleared, we can reschedule the flights. And maybe those flights that were going to be cancelled are no longer cancelled, because, we know, most likely by 9 o'clock the fog is out, okay? Yes?
2 questions. I'm also in high-performance computing, and how do you do the progress monitoring? So how do I know when I submit a huge job that's being dispatched out there? How do you do the progress bar? And then the second question is, will your code be publicly available?
Okay, so our model, the IFS, is not publicly available. How do we do the progress monitoring? there's another system that we have, also built, by the way, in C++ and using boosts, which is a flow, is a data flow, kind of a task scheduler that manages the whole flow of the operational cycle and resubmits tasks that then go to the HPC cluster scheduler. But then we have hooks in the model that talk back and say where he is at the moment. So we know if the steps are going in. And those hooks actually also trigger the post-processing. So yes, you're right, this is an issue. And what was your other question?
About the publicly available.
Publicly available. So what's not publicly available is the IFS, the model. But usually the tools around it, they are. And this project that we are doing here, once it gets mature enough, we probably are going to open source it with Apache license.
So just in terms of the question about are large scientific Fortran code sustainable, there used to be a time, at least within the US, there used to be a time when you could write a grant and get money, and you didn't really have to talk in your grant about software sustainability. It was sort of like, we're going to develop this code, it's going to do this thing, it's going to generate results, and then there was you didn't really have to think about what's going to happen in the code afterwards. That is no longer the case. These days, if you want to get money to develop a code, your proposal needs to talk about how is that code going to be reusable, and how is it going to be sustainable, and what's going to happen to it in 30 years from now. And so this is one of the reasons why you see a lot less new proposals for, hey, let's go develop a Fortran code, because I think it's really hard to sort of with a straight face say, we're going to develop a 2 million line Fortran code that's going to be a modern, reusable library that's going to be maintainable for the next 30 years. I mean, for one thing, it's just hard to find Fortran developers, to find like young people who want to write Fortran code.
We have lots of them. We are going to slowly refactor our code base, but it's not going to be a dramatic change from one day to the other. We're not going to start from scratch. We are going to slowly, and the reason is because it's an operational piece of code, runs every day. The space shuttle was launched every so often. You don't have a fleet of space shuttles all the time up there. So that's why it's a very different thing. Yes?
Yeah, I was wondering in your model if you have a way of comparing predicted versus actual results and then feeding that back into your algorithm to fine-tune your algorithm.
Yes, we do. It's called reanalysis. So we take the data of the past, we feed it to the best model that we have today, and we run. And that computes, I'm not the expert in the matter, but that computes some scores, right? That gives you an idea if your parameterizations are good or not. Because then you know what happened, right? And then you help adjust the values. And that improves your next forecast because your model, so you are totally right. That's exactly what we do.
Let's just take these two more questions.
So I was kind of surprised that the same people who are kind of scared of programming in C++ would be open to programming in something that looks like Haskell. I was wondering if you could comment on that.
Aha! No. Yeah. Very good question. Very good question. They aren't. They are not going to see it. I didn't explain, I didn't go into that detail, but we are going to put on top of this a Python interface, which is something they are not so against. And for those that want to contribute actual code that runs, they are going to program in Fortran plugins that we wrap around with the C++, and then we provide the expression that represents those in the language. So they will never see the language. But the language is our vehicle, okay? It's our glue, it's our indirection. Yes?
How helpful are large-scale meteorological events to helping your algorithms predict weather patterns, such as Hurricane Sandy?
I'm sorry, I didn't understand correctly the question.
How helpful are large-scale I can't even pronounce that word. How helpful is Hurricane Sandy to helping your weather prediction model? So
what we do, that's called extreme forecasting, okay? Extreme forecasting is a bit, because it's extreme, is out of the norm, right? So we revisit those storms. Especially Katrina was studied a lot, because actually in Katrina we didn't do that good job, okay? And we study it and we change our models and we see, would we have done better if that would happen again, which doesn't happen. So we revisit a lot of things, and we try to recalibrate them, and yes. And then we have special processing streams of our data, and even indicators. So in that website that I showed you, you can actually plot the extremeness of the weather on that position. How far from the average that we know of the last 20 years, how far are we from the average? So, and I can tell you, for example, and we have heard that Colorado this week has had out of average weather, yes? So how do we know those things? We know those things because we have the data. That's why the archive is so important. We go back to the archive and we look at it, we do statistics with it. Again, those statistics are things that can be done in this language very well because they are basically embarrassingly parallel. Revisit 20 years of data, recompute all these statistics, and get me some numbers. And then you plot the number in a map. So yes, we do look at those things very much.
Thank you very much.
Okay, thank you.